Hello, everyone. Welcome to tonight's edition of the FRC workshop series here in Australia. I hope that you all had a great weekend. And tonight we're really happy to have Jonathan from Normanhurst Boys High School. He's a mentor there. I believe he was a student on that team for a while. It's team 4739, Control F5. And he's got a really interesting topic prepared to talk to us tonight about. He's going to talk to us about how to do FRC on a budget and in a short amount of time, which is something that I think is really critical for a lot of teams here in Australia. So thank you. Welcome, Jonathan, and I will turn it over to you.
Thanks, Noanne. So today we're going to be talking about building on a budget. So specifically how to be competitive with a limited time and limited budget. So budget, not only financial, but also in terms of how much time you actually have with the robot. So before we begin, let's imagine a scenario. So it's January 2021. You have been eagerly awaiting to watch the kickoff event. Obviously, we don't get a new game, but you're looking forward to seeing what the rule changes are and eagerly awaiting with your team to brainstorm ways to improve your robot and be even more competitive in 2021. And you watch the game, you see what's going on, and then someone tells you there's a bit of bad news. You only have $1,000 to work with and 5 weeks of access to your robot, and only 10 people in your workshop at once because maybe COVID restrictions. So what do you do to prevent this season from becoming an unmitigated disaster? So that's what we're going to talk about in our presentation today. How to be competitive with those restrictions. So who is this talk for? Well, really, it's for everyone. Now, you might not be a team who's particularly pressed on your budget, and if by some fortune you're not affected as much by the pandemic, that's great as well. But everyone is looking to improve their productivity. So this talk is for teams who have smaller budgets, limited access, and if you're just looking to try and do more with less time. So what are we going to talk about today? So this talk will be broken up mostly into 3 parts. First, we're going to talk about team organization, then robot architecture, and finally, we're going to jump into how the actual design and manufacturing of your robot can help you build it a bit faster. And the reason that I've decided to structure things like this today is because when we typically think of how to build your robot faster, we generally only think of the last point. However, in my opinion, that last point, it can be argued is maybe the most minor of these 3. And the first two points they're all important, but in particular, the first 2 is where, at least in my experience on my team, we haven't been as effective as we could have been. Now, just remember as we're going through the things that we're going to talk about, that all 3 of these aspects intersect, they work with each other. So be creative in how you leverage all of these. None of these 3 things can exist really in a vacuum. Okay, things that are beyond the scope of this talk. So things that you need to go and figure out yourselves. Finer details. So finer details on robot design, on team organization. There are so many resources out there created by the FRC community. That's on YouTube, that's on Chief Delphi, or many other platforms. Those cover a lot of things better than I can cover them here. And I'll show you where those things I've included where you can find those things when I talk about the relevant topics. And also how to implement this on your own team. Obviously, everyone's requirements will be different. Just because I make a suggestion doesn't mean it'll necessarily work for you. make sure that you critically analyze and discuss with your team whether any of the suggestions that are in this presentation are applicable and are useful to your team. Okay, so let's talk about the first thing, team organization. So this is about how you run your season, how you run your team, and how you work together to actually build your robot. Okay, first of all, know what things you're working with. So as soon as you have a rough idea of what you have to work with, make sure that you get this plan up. So do this definitely before the season. Now, obviously, with COVID and moving goalposts, sometimes unexpected things might happen. We can't really know what they're going to be, otherwise they wouldn't be otherwise they wouldn't be unexpected. So do this to the best of your ability. Figure out all of the regulations around when you can build and how you can build. So sometimes if you're a community team, that might be in the form of government regulations on how many people can be in a room at a time. Or if you're a school team, then the department might themselves have regulations on after school activities and things like that. Make sure you figure all of those things out. There's nothing worse than thinking that, okay, we have this amount to work with, and then finding out, oh no, we don't actually have this amount to work with. That would throw a real spanner in your works. So make sure you know these things. How many build days can you have? How many people can actually be there on any one day? On any one day, rather. How many or where can you meet? Is this somewhere that you have access to machinery, or is this going to be just someone's garage? And of course, who can use what tools? Because if you have a bunch of people turning up and none of them know how to use the tool, that one specific tool you need, or that one specific machine, then that's not going to do you much good. Now, figure out how many man hours you have. So that's the number of people multiplied by the amount of time that you have. And if you don't like the word man hours, you can call it woman hours or people hours or whatever else. But that's the general concept. And this is a very good measure of how much actual time you have. Remembering that time is, in most cases, your most precious resource in a build season. Okay. Second thing is to distinguish between soft and hard time. And if you take nothing else away from this presentation, I think this might be the most important thing, because this fundamentally changed the way that my team approached build. So soft time is times when your team can meet, not in person, but online. So we first came up with this idea because we've always been a small team. We've haven't had very many teacher mentors, and all our teacher mentors, they gave a lot of their time very generously, but we can't demand them to open up the store every single day during the holidays so that we can meet. That simply wasn't practical, and it would be quite unfair on our teachers. So it was back in 2016, 2017 that we came up with the idea, hey, instead of starting the build process in someone's garage or where conditions might not be the most optimal to build, why don't we meet up in a library or call online? And we can use that time to strategize, to design, and research, planning, all of those things. So we call that soft time. So time that we can spend together as a team, whether in person or online, but just not with access to the robot. And obviously, in the past, that's been a challenge that's been quite unique to our team. Well, when I say unique, I assume it wasn't widespread. But more and more now, in everyone's present circumstances, this is going to be more of a factor in every team's deliberations, because meeting in person is now a luxury. So use your soft time to plan out how you're going to use your hard time. So that's times when you can access your shop, when you can actually do physical machining, when you can actually work on your robot. And this is going to be your most precious resource. And never do things in hard time that you can do remotely. So one rule that we had was, if we're in the shop and we encounter a problem, and that problem involves going back and looking at designs, looking at, oh, maybe we need to adjust this there, adjust that there. Even if it would take 5-10 minutes to figure out what to do, we never did it. We never did it there. We'd say, forget about this for today. We'll figure this out once we get home. So that's our rules with soft and hard time. And as I said, if you take nothing else away from this presentation, make sure that you use your hard time as effectively as you possibly can. All right. So how do we actually use our hard time, the time that we have access to our robot? One thing that we decided to do was go for shorter and more focused days. So I hear stories quite often about many teams, many very enthusiastic teams, pulling 8-hour, 10-hour, 12-hour days. And one thing that we quickly realized was the law of diminishing returns kicks in. And we found that it really kicks in around the 6-7 hour mark. And after that, people start taking longer breaks. People start working a bit slower, getting tired. And so we decided we're going to go for really short and really focused days. And part of that was also when we had access to the school. So, for example, on weekdays we would try and go for 2 hours after school. And 2 hours, as soon as the bell rang, you got to our shop, and we jumped right into it and didn't do anything else for 2 hours. At the end of the 2 hours, packed up, and everyone was going home. So in terms of efficiency, that is to say how much work you are doing in those 2 hours, the shorter the day, the higher your efficiency will be. Now, another big part of having very limited access to your robot is you have to CAD as much as possible. So there's many talks on YouTube about why CAD is so important. And especially with limited access, you can't afford to be making major mistakes. So you can't afford to have a facepalm moment where you go, oh no, the intake is too large to satisfy the frame perimeter extension rules. That would be an absolute disaster if you don't get much time to work on your robot physically. So resolve all issues in CAD. And of course, this will never be perfect. And if you speak to anyone from my team this year, they'll tell you all of the troubles we had. And this year, we CADed more than we ever did before. We literally CADed in nuts, bolts to make sure that everything cleared. So CAD as much as possible. Next, appoint a shop manager. So this person should be a responsible student or a mentor whose sole job is to make sure that people are working efficiently and making sure that needed resources are getting to where they need to be. So if a particular task is falling behind schedule, allocate some extra people to there. If there's a bottleneck, find a way to clear it. So we found that after we had someone begin acting as a shop manager, our efficiency also skyrocketed, because all of those bottlenecks, all of those places where before we got held up, those could be cleared a lot faster. And finally, just 2 points on being organized. Have an agenda. So don't go into a build day going, we're going to build a robot today. Instead, we found that if we listed out each and every task that needed to be performed that day. And often this will fall under the responsibility of the shop manager. Our shop manager, he would figure out, okay, what things we need to do that day, and allocate people with the requisite skills to each task. And then we would try and hold meetings. Now, we didn't always hold them the night before. Sometimes it was right at the very start. But we would make sure that everyone knew exactly what task he had been assigned to, or had been assigned to him rather, and what sort of things that they would be expected to do that afternoon. Now, make sure that you are reasonable. Don't tell people to build half the robot on their own in a day, and be flexible because things will run over time. Some things will take longer than expected. Some things will take shorter than expected. Although, speaking from personal experience, the former tends to happen a lot more than the latter. So be prepared to reallocate people where need be. Okay. So this is what I think most people's robot development processes will more or less look like. And I've included on here where you would use different types of time. So strategy and design, mostly soft time. If you're going to prototype, and I know that not every team gets to prototype very thoroughly, and that's okay, because you can substitute a lot of prototyping by looking at past game pieces, looking at how other people have prototyped and the videos that they've put on YouTube. So try and do that within the first 2 weeks. Now, week 3 and week 4 is usually when schools start opening. So that's when holidays start finishing. And if you're a store team, that's usually when you'll have more access to your school and to your robot. That's when you start fabrication and assembly. So during fabrication, that's the name that we give to where you knock out all of the parts, the raw, so cutting your metal stock, drilling the necessary holes. We call that fabrication, and assembly is putting all of that together. So I'll talk about the differences between fabrication and assembly in a second, and how you can make those as efficient as possible. And finally, make sure that you leave yourself some time to test. And it may seem a bit weird. Okay, surely, what does testing have to do with productivity? Well, the end goal of productivity is to be effective and to be competitive. And testing and tuning is essential to that. So make sure you leave some time to do that. Okay. The next thing that you can do to make things more efficient is to formalize processes. The number one enemy of productivity is mistakes. It is not, I should say errors rather than mistakes. So the difference between errors and mistakes is mistakes tend to be things that where you've made a misjudgment or something like that. Whereas errors, we tend to think of those as somewhat unavoidable. They're just things that creep in. So the number one enemy of productivity is errors. So having formalized processes helps you get into a routine or a rhythm. And there are many studies that have shown that once something is habitual or rhythmic, it's much more difficult to make careless errors. So set up a formal review, approvals, and revision process for your designs to make sure that that little bolt that you didn't notice collided with your arm or your elevator. Make sure that bolt that collides gets spotted. And that's best done through a review and approval process. And definitely use engineering drawings. Engineering drawings to accompany each part make sure that the features of each part are clearly communicated when you're manufacturing it, and to make sure that you don't drill a hole that's sort of in the wrong place. And finally, consider using a production line approach when you're actually making your parts. And that's the next thing that I'm going to talk about. So generally, this is something I haven't seen done very much within FRC. And this is specifically targeted at teams who mainly do their fabrication through manual processes. So sawing, drilling, and basically if you don't have have access to a CNC. So the way that we've tended to do this in the past is we found a day when we can get a lot of people into the shop at once, and we usually do this spread out across several rooms. So in one half of one room, we'll have people cutting the raw stock to the parts needed for each part of our robot. So be that square tube, rectangular tube, angle, whatever. Then we had a team of dedicated people who made marks, so who marked out where you needed to put the holes based on the drawings that were handed to them. And so each part then moves with its drawing from one station to the next. So after the marking station, it goes to the drilling station. Once again, 2 to 3 people who look at the marks that have been made, look at the engineering drawing, and drill the holes as need be, and then so on and so on, special features and finishing touches. So what we found with this approach is, because everyone is doing the same thing over and over again, people get into a rhythm. They're very focused on their task, and this way the people don't have to run around looking for drill bits or any of that stuff. Things get done very, very efficiently. And I'll come back to this point later on, but we found that usually it takes only 2 days to get all of the parts for our robot made using this method. Okay, so how do you do this? You divide people into different groups. You can put them in different rooms and this is a good way of overcoming COVID restrictions. If there's a rule that says you can only have X amount of people in one room, well, you can use multiple rooms to divide up the stations. Now, divide people up by what they're good at and what they want to do. This is another good way of giving people what they want. People tend to be more motivated when they're doing something that they like. Again, your shop manager will be an important role in this job, or in this system rather. So they have to identify production bottlenecks. They need to go around making sure that everything is going smoothly. And part of their job is also to decide who's the best for each job. Of course, they need to balance that with what people actually want to be doing. Okay, and of course, make sure you have the flexibility to redistribute people to where they're needed. Okay, and finally, this may seem a bit odd in a presentation about, ostensibly a presentation about how to do things faster, a culture of safety. Now, we hear a lot about safety in FRC, how it's very important, but one thing that people don't tend to mention is the number one worst thing that can happen to your productivity, even worse than major errors in your design, is if someone gets hurt, because the whole process grinds to a halt. Teachers, mentors, and students are needed to make sure that the person is okay. And above all, you just don't want people getting hurt in general if you care about your team members. So prioritizing safety is actually a really good way of improving or reducing wasted time. And safety does need to start from the top down. So team leadership needs to take initiatives to promote a culture of safety within the team. And of course, those of you who know my team know that this is definitely not one of our strengths. It's something that we've been trying to work on for many years. And so speaking from experience, if your team is not safe, this will cause huge delays. Okay, so that concludes our talk on team organization. So now we're going to move on to robot architecture. So what things can we do within our robot system design to make it easier to build? So first thing is what is robot architecture? You may not have heard of this this term before if you're a bit newer to FRC. So this is the big picture design of your robot. It's very closely connected to to strategic design, rather. So this is about what mechanisms you're going to put on your robot, where they go, and how those mechanisms work with each other to make your whole robot work. So it's things like, I'm going to have a lift here, I'm going to have an arm here, and I'm going to have an intake out the front. So one thing that our team's analysis has revealed is, firstly, that we design robots rather way more complex than we really need to have done well in that specific year. And the more, looking back at every robot that I've been a part of, so I've been around for about 5 years now, every robot that I've had a part in building, we've had some mechanism or we've had some design feature that simply wasn't necessary. And perhaps if we hadn't had that feature, our robot might have worked even better. So, and this is something that we see in a lot of Australian robots, because, well, I don't know if there's a specific reason for it, but that's something we've noticed. So we've now, one of the ideas that I've had is, at the start of every season, when you look at the new game, the first question you should ask yourself is, can we get away with playing this game with just an arm and an intake fixed to that arm? And I would move to suggest that in the majority of games that we've seen in recent times, the answer to that is yes. And most of the time you can do actually quite well with just an intake and an arm. So let's have a look at an example of this. So here are two robots from the 2019 season. So those of you who follow the big leagues, so to speak, over in the US will instantly recognize the robot on the right. However, the one on the left can be said to be a little more obscure. So if we actually take a moment to just analyze at first instance the architecture of the robot on the left. So and you can search up this team on Blue Alliance and look at some of their matches to see how their robot works. It's quite simple. They have a hook at the front of their robot to collect a hatch panel, no ground pickup capability on the hatch panel. They just pick it up from the driver station or whatever it was called that year. And they have a single arm on one pivot with a row of wheels that picks up a ball from that year. And there's a hidden feature that you can't quite see, which is there's another arm underneath the robot that deploys to lift it up and flip it onto the HAB platform. That's the climbing aspect of that year's game. So in total, this robot has two single jointed arms, each one powered by nothing more than a simple motor and a chain, and one little hook at the front to collect a hatch panel. The robot on the right has a turret, claws, a lot of things. Technically, it's a very, very impressive robot. And of course, both of these teams did a lot to pull their robots off. So you may ask, well, why are we comparing these two robots? Well, let's have a look at their competition history. So I've chosen the two regionals that both of these robots competed at. So they were both at both regionals. So the first one, San Francisco, you can see that 604 actually outranked 254. So remember which one is 604? Okay. At Silicon Valley, they weren't far behind. So the point is am I claiming that the simple robot with 2 arms and 1 hook is better than the beautiful machine that we see on the right? And no, that's not what I'm trying to say. I'm trying to say that a very simple robot can be very much competitive with and be impactful in the same competition as what is a technically very advanced and very impressive robot. Okay, so why was this robot so effective then? 4 big points. 1, good strategy. This team saw that it could do more by doing less. 2, they played it smart. They didn't try and pack in as many features as they possibly can. They just did the simplest thing that they could to get a way to achieve the goals that they set. 3, they used COTS parts and very simple structures. So if you look at their robot photos on the blue lines, you see it's just a lot of right angles, a lot of VersaFrame, and Versa Dussets, or whatever they're called. And so by saving resources, both money and time, on new robot functions or more advanced robot functions, they spent more time on practice and refinement. And that helped them be one of the fastest scorers on field at both of those regionals. Okay. So we can combine that with a few things that I've learned myself from my years in the sport. So the number one biggest mistakes I've seen teams make, and indeed my own team make, and we are a prime suspect for this, is overcommit. Every year people go, I want to build the most awesome robot imaginable, and this year I have the resources to do it. Except everyone's an optimist at the start of season. And so we often find that we overcommit and things don't really get done to the standard that we really want them to. Fewer functions equals better functions. The less things you attempt, the better you'll be at it. And this is something that we've only come to appreciate recently, because what we've always believed, or the third point rather, is something that we've only come to appreciate recently. We've always believed that the point of having fewer functions is that you can add more advanced features to those functions. So for example, say for example, this year we decided, and we didn't actually decide, this is hypothetical. So say for example, this year we decided, okay, we're not going to worry about climbing. Let's just make a shooter. But because we're just making a shooter, let's make it the biggest, baddest shooter that we can possibly make it. It'll have a turret. It can shoot on the move. It can shoot from across the court. No, that's not the point of it. So one thing that we often find is if we just give the actual mechanism, have fewer mechanisms, and also have mechanisms that perform fewer functions. So we find that often having a turret will actually slow a team down because they're busy adjusting their turret. Whereas if they had just not done a turret, they would have had extra time to practice aligning without one. Similarly, lifts tend to be more complex than arms. The added benefits, the geometrical benefits of having a lift, are often offset by just having more time to practice if you just have a simple single joint arm. And the final thing is avoid having mechanisms that pass game pieces to other mechanisms at all costs. We've tried to do this before. We've seen many teams that have done it before. It can definitely work, but in our experience, it's just been too much of a resource drain for the marginal benefits that you get from it. And often the reason why you would do that is so you have less weight on a mechanism. But we found that, sure, if that mechanism has to go a bit slower, that's even better than all of the trouble that you sometimes face by doing this. Okay, additional resources. These are both great presentations made by world-class teams, much more experienced than myself. And I would strongly suggest that you check these out. Okay, so to recap for robot architecture, manage expectations, do less, leave more time for practice. Okay, the final part that we're going to cover is mechanical design. So these are things that are more traditionally thought of in relation to how to build robots faster. Now, I suspect that the majority of things that are in this part your team has thought about before, so I won't dwell too much on many of the points here. The 4 S's: simplicity, serviceability, separability, and standardization. I was unfortunately not able to find another ility that fit into the 4th. So simplicity, this is pretty self-explanatory. Less components, less complex structures, reduce the number of fasteners, reduce the number of joints. Every saving you make here is going to reduce the amount of time you need to manufacture. So remember back to what we were talking about with hard time versus soft time. By not physically meeting to discuss design, etc., you should actually have more soft time. So that's more time you have to refine your design and make it simpler to build. And also, just try and at the end of the day, simplicity is also just comes down to trying to use less stuff. That's going to save you money. That's going to save you time. Okay. Serviceability. Make sure you put lots and lots of access holes. So likewise, just like the shop manager, appoint someone who is going to consider manufacturing, preferably someone with a lot of experience building robots, maybe a more senior member, a more senior student on your team who has had their hands dirty from building lots of robots in the past, and they know what sort of holes are easy to access, which ones aren't. This year we didn't do this particularly well. This year we ended up having an electronic board that's underneath our shooter, and to access it, you had to prop the robot up on 2 chairs and have 2 people underneath the chairs lying on the ground looking up, one holding up a spanner, the other one fiddling with a piece of wire. It was a nightmare. Don't do this. Whatever savings in space, it's not worth the time. And also, if you're building a simpler robot anyway, you shouldn't have too much of a space problem. So consider manufacturing and repair at every turn, because not only will this save you at comp, this will save you when you're at home and you need to make changes, or if you need to repair something during testing. So appoint a manufacturing specialist and invest in a few useful tools. Don't go out and try and get every tool underneath the sun. One thing that we've been trying to do is we've been trying to standardize our bolts and just get 10 Allen keys that are that one specific size. So no one has to go around asking for, oh, have you got that specific Allen key? Have you got that specific spanner? Just have standardized tools and have lots of the same size. This will help free up bottlenecks during assembly. And also, once again, on safety, if you have poor access, you're more likely to have mishaps and accidents, things not installed properly, people getting hurt, which is even worse while installing things. This is going to slow you down heaps. So this is what I was talking about. Do not do this. So this is where we put our electronics board underneath our shooter. As you can see, this is the antonym of ease of access and serviceability. Okay, finally, well, not finally, rather, separability. So one thing that we have done well this year is making mechanisms be entirely modular so that they can be assembled not on the robot, but by themselves. So what you see on the right here, pardon me, is our shooter assembly. So our conveyor and shooter together. As you can see, this is entirely this is entirely modular. So it connects to the frame of the robot by 4 bolts. And so if ever we have a problem with it, we just undo those 4 bolts, it'll come out, and it doesn't impact any other part of the robot. So doing this means that you can have multiple parallel processes of assembly. And so if one subsystem fails, then you can easily take it out to repair. It doesn't impact everything else. So it's as much of a lifesaver at comp as it is in the workshop. Modularity is very important, in my opinion. And last thing, standardization. So make sure, just try to standardize everything. That's the gist of my advice. The more standard your things are, the easier things are for at every turn, basically. So you can see on the right. So this is hand drilled. This is not, we don't have a CNC that does tube metal. So this is all hand drilled. And so all of the holes are the same size. And they're also like they're also the same interval. And so this whole piece, what you're seeing here, is the tall part of our shooter. And this in total took maybe 5 minutes to drill because everything was standardized. We used a jig. And so it was just hole, 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 hole. And there was no need for any sort of fuss with trying to figure out non-standard hole sizes or non-standard hole placements. And so this also saves a lot of time. It also means you need fewer tools and fewer parts to interface. And not to mention, I haven't put it on here, but it saves a lot of misunderstanding and parts manufactured incorrectly. All right. So what things can you use to help with standardization? So holes in particular, and this is again specifically aimed at teams who don't use a CNC to manufacture, who have to drill things by hand. So whenever you drill something by hand, you want to make it as regular as possible. So there's 2 ways of doing this. So one is a centralized process. So that's where you have all of the pieces fed to one person or maybe 2 people on a drill press. And that's what we did this year. So if you look on the right, that's a drill that's very similar to the one that we use. And so on the bottom, you can set up the guides so that it's in the correct alignment, and you just slide the piece along to where the hole needs to be lengthwise, and you drill that, slide it down further, drill the next hole, etc. So that's a centralized process. What we're looking to move to next year is a distributed process where everyone gets a jig. So this one on the bottom, you can get this one from Aussie Boards, and I think we do intend on getting ourselves one later on. And you can use this. You can give this to a few different people, and so you can have multiple people at once drilling holes in a very precise manner. And if for whatever reason you want a different specification to ones that you can get from Aussie Boards or from ThriftyBot, you can always 3D print your own and just purchase bushings from the internet. Okay, so COTS and outsourcing, and I think this is probably the last substantive point that I have to make. So COTS and outsourcing, if you're on a budget, buy more, not less. And this is a lesson that I know our team definitely learned the hard way, and this is one place where we've gone wrong in the past. So why should you buy more if you're on a budget? Well, the answer to that is it saves you a lot of time, and it helps to simplify things overall. And if you're on a budget, then you shouldn't be looking to build the biggest, fanciest robot out there in the first place. And if you buy more stuff, it will save you time, and you can recycle that stuff year on year. So shop around and find a good deal. So there's many smaller vendors out there, Aussie boards, who are based locally, Thrifty Bot. So look beyond just Andy Martin Vets. Those guys have great products, but as do these smaller vendors. And often you can get very similar things for a considerably lower price. And this third point is something that we're also thinking about doing in the future. So if you're very pressed for time, you can actually outsource manufacturing to a local CNC shop. So this may seem like a bit of a weird thing to do if you're on a budget, but just like buying COTS parts, well, although this is sort of the opposite of getting COTS parts, this is getting some custom-made structure, you can actually save on the number of parts that you need to purchase by getting things CNC machined. So as an example, this year we had to actually get a lot of things to make our shooter work. And afterwards, as when we were doing our season review, we realized that if we had utilized a CNC shop that was just down the road from where we're based, we could have saved on not buying a gearbox. We could have used just belts or chains to do many things. And so definitely have your wits about you, so to speak. Explore different possibilities and see whether actually getting things CNC machined by a local shop would actually be cheaper. Not to mention, it is going to be a lot faster because now you don't have to go and cut metal and assemble things. So starting next year, we're going to be building robots in a hybrid CNC and tube metal architecture. So whereas in the past we've used almost exclusively tube metal, we're going to try and move away from using lots of bearing blocks, because bearing blocks are expensive. Bearing holes are much cheaper if they're machined into the part themselves. So once again, that's an unconventional way to save money. Okay, so where does this leave us? So this on our right is our partially constructed robot. So we applied many of the principles that we mentioned in this presentation today to this robot that we built at the start of this year. So the structure, that's including the drive base, everything, this took 60 hours to fabricate, 60 man hours rather, to fabricate. Assembly took a fair while longer because we didn't do that bit as well as we wanted to. So it's worth noting, so if we think about 60 man hours, that sounds like a long time. But if you have a team of 10 people, and 10 people isn't that big for an FRC team, if you have a team of 10 people and you stick them in a workshop for half a day, 6 hours, you will have had all of the metal, all of the holes drilled, deburred, and even brushed to be able to manufacture this robot, to be able to assemble this robot rather. And so if you think about it, that's really not a lot of time if you just have 10 people in a workshop. Okay, and that concludes the structured part of my presentation.
Thank you so much. That was amazing. We've had a lot of comments come through that very, very complimentary on the information that you presented. So thank you. We do have a bunch of questions tonight. So I'm just going to kind of go through them. The first one is, how big is your team and how many mentors do you have?
Yep. So our team this year, if I remember correctly, on the rolls, we had, I think, 15 at the start of the year. And one of the great things about my team, if I may indulge in praising my team, is that all 15 people turn up to build. And so we had 15 on the rolls and effectively 15 pairs of hands. and our design team is about 4 or 5 people. So in terms of mentors, so we have one teacher mentor and myself, who this season, yeah. So we're not a big team by any means, but that's part of the reason that we've learned to do things more efficiently.
Excellent. So the next question is, do you have a written process for your approval system that you could share with other teams?
So in terms of written process for approval, so in fact, if you, I don't know if we have a written process per se. However, one of the other teams, one of the other members from my team, Evan, he did a presentation a couple weeks ago on collaborating using CAD, and in that he talked about the approvals process. But to recap it very quickly, what we do is we assign different mechanisms to individual designers, and those designers they'll make their first iteration. We'll try and put it on the robot, and a mentor or other students in the design team, we will look at each design system. Look at each subsystem, and we'll see if there's any obvious problems that we see, any things that we suggest might be improved, and we keep on working at this until we get to a final solution that everyone is mostly happy with, a final design.
That's great. Thank you. The next question is, do you go metric on standardized nuts and bolts as the kits come in imperial?
Well, this is likewise something that we've debated a lot about. So it's a bit weird in that for standardization of nuts and bolts, we are on imperial. So we go with the 1032s that come in the kit just because we have an awful lot of them. However, the holes that we drill are standardized to metric. The distances between the holes are standardized to imperial. And so this may sound a bit funny, this doesn't really sound like standardization, but the way that we justify that is all of our linear distances are in imperial, and all of our diametrical distances are in metric. And because we use different tools to measure those, and so therefore we get away with having standardized things that really aren't standardized, but in practice have all of the benefits of standardization. However, having said that, next year we are going to all metric because it just causes headaches sometimes.
Great answer. Another question is, how do you find the balance between perfecting a particular mechanism and leaving time for driver practice?
That's definitely a balance that is difficult to find. So, and I will admit that I don't think our team has found that balance all that well in the past. And so what we're going with at the moment is we want the mechanism to be as complex as need be to achieve what I consider the basic unit of function. So we try to avoid advanced features like self-centering or turreting. So that way we get as much time as possible for driver practice. So I would say for our team, in the future, going forward rather, we want to be tipping that balance more towards less complex and more driver practice. Although this will vary from team to team. So I would say that as a team, you need to have that discussion and decide based on your own particular circumstances how how many good design members do you have, and how much time and access to a field do you get?
All right, the next question has to do with drive bases. Would you suggest building your own drive base instead of the kit of parts to get the Andy Mark voucher?
Once again, not an easy question to answer, and we've dabbled on both sides of this one. So there are definitely benefits to using the kit of parts drive base, and if you look at Chief Delphi discussions, everyone sings the praises of the Andy Mark drive base till the cows come home. But in many ways, I think if you are working with a limited budget, say $1,000, $500, having that extra 450 USD of Andy Mark parts really can help a lot. So I think once again, it's a matter for teams to decide. I would move to suggest that if your team has skills, or if your team has a lot of very skilled members, then perhaps, and especially this season, building a custom drive base might be the way to go. However, and that is also assuming that you have ample time and access to your workshop to be able to build a simple one. Please do not build a Mecanum or a Swerve, just West Coast Drive, and versus using an Andy Mark drive base. That might be something that tips it in the favor of building your own. On the other hand, one thing that you can do is you can simply use last year's drive base. And if the rules change in future such that you need to actually build it in the season itself, just disassemble it before season and put it together on the first day that you build. If I understand the other rules are correct, that should mostly satisfy the rules. So those are both ways of getting the Andy Mark voucher. One reason why you might just opt in for the drive base rather than the voucher is if you are very much very strapped for time and your team is relatively inexperienced, having a solid working drive base and just having simpler robot mechanisms is never a bad thing.
Great. Another question has come in the chat, which is, does your team use simulated driver training on virtual robots?
We've tried it. I can't say that we particularly like it. I think there's definitely some things that can be taught virtually. And one area where I think maybe we will experiment in future is practicing I think the proper word for it is fieldcraft. So that is to say, playing around defense, the maneuvers that you can make with your robot to get around defense, especially if you want a full field. So if you want a full field of 6 robots, it's quite difficult to get the experience of a full field with 6 robots and all of the clutter around that without actually having 6 robots. So I think that's one place where we might use driver training in the future. However, one of the things that I think is where driver training doesn't quite cut it is getting a feel for the actual handling characteristics of your robot. That's a big thing. And I guess before I was in FRC, I was a huge fan of motorsport. And one of the big things in motorsport that they do on the testing days is they want to get a feel for the dynamic characteristics of the car. And that's a function of your robot's weight distribution, the types of wheels you're using, and the configuration of your wheels. So to actually, if you're looking to up your game when it comes to how well or how precisely your driver controls your robot, then I would suggest that maybe in-person, like actual driver training on real carpets would be the best way to go. However, if what you're looking to improve is how well your drive team works together, or how well your drive team responds to the actions of other robots on field, then simulated driver training might be a very effective way of going about that.
Great. So I think that's all the questions that we have right now. Do you have any closing remarks that you want to make?
Well, I guess in closing, to reiterate the 2 points that I hope everyone takes away from this presentation. One is make sure that you use your soft time and your hard time in the most efficient way possible. And two, do not overcommit when it comes to robot function. If you do those two things, you're going to have a pretty successful season.
That's great. Thank you so much for the presentation tonight. I think it was incredibly helpful to many, many Australian teams. And, we're really looking forward to seeing your robot whenever it is we all can get together again. I also just wanted to acknowledge we had a couple of FTC teams joining us tonight, which is great as well. So we had both FRC and FTC teams watching, which is wonderful. And finally, I want to thank the people who are behind the scenes here as usual. Tonight we had Ian from IC Robotics, who was helping out and making sure that everything ran smoothly. So huge thank you to Ian and IC for all of their help tonight. I hope you all have a great night, and we'll see you next week. Bye.